Dr. Mungi, and today we're going to cover resultant forces and distributed loads. So for today's outline, we're going to talk about what distributed loads even are. Then we're going to talk about magnitude and location of resultants of distributed loads and how to find them. We're going to go over a quick example. Then we're going to talk about common types of distributed loads in civil engineering applications. And then I'm going to leave you with a practice example so that you can try this on your own. All right, so what exactly is a distributed load? Well, a distributed load is a loading that is distributed over a surface, so kind of exactly what it sounds like, okay? Some real-world examples are pressure of the wind on the face of a stop sign, or pressure within a water tank that is distributed, right? So you'd see the water inside exerts pressure on all sides of the tank, and that is a form of a distributed load, and also weight of sand on floor of a storage container, okay? The pressure exerted at each point on the surface indicates the intensity of the loading, okay? The units of measurement that we typically find for distributed loads are in SI, the Pascal, which is 1 Newton per meter squared, or in US customary, PSI, which is pounds per feet squared, okay? Start by drawing a couple of diagrams, and then we're going to write the formula for the resultant force, okay? Let's start with drawing a type of beam, and we're going to draw some general loading that varies along X. Let's say X is measured from this initial starting point. Let's say the entire length of the element is L. I'm going to call this W of X. It's basically W, the distributed load, but it varies along the length of the element, so I'm going to call it WX, okay? And I'm going to draw a corresponding element here that signifies what the resultant force is. So if I have the same beam and I have this distributed load, everything under this distributed load is defined by some area. There's some area here. And I have the resultant force, which acts at some point, right? We don't know what that point is just yet. But we have this resultant that acts through the centroid of this area. And we also are measuring from point X, and the entire length of the element is still L. So we're actually going to come back and do what we love to do in these derivations, and we're going to isolate a little tiny dx. Okay? And what we're going to do here is I'm going to write the formula for FR, okay? FR, which is the resultant force. This is the magnitude of the resultant force. We're going to apply equilibrium, so we would have the integral over L of Wx dx, and this is actually just equal to the area under the curve in this diagram. So basically what we see here is that the magnitude of the resultant force is equal to the area under the loading diagram. Okay, this is the important takeaway. Magnitude of the resultant force equals the area under the load diagram. This should ring a bell from when you're doing shear and moment diagrams, or what you kind of learned in your previous classes. This should kind of ring a bell now, I'm hoping at least, okay? Now, how do we find where that resultant force is located? Now that we know what the magnitude is, how do we find the location of the resultant force? So I'm going to write down that formula for X bar, okay? And this is basically the location X bar of the line of action of FR, that resultant. And this is determined by equating the moments of the force resultant and the parallel force distribution around point O, which is the y-axis. So we're taking the moments about point O, which is that y-axis, and we get this X bar. We get the integral over L of X, and I'm going to tell you what all of these are in case you forgot. Divided by the integral L Wx dx. And this can be simplified as the integral over the area of x dA divided by the integral of just dA. Okay? Now, if you remember, so this coordinate x bar, this locates the geometric centroid of the area under the distributed loading, okay? So this is the geometric centroid of the area of the area under the distributed loading. Okay. In other words, the resultant force has a line of action which passes through the centroid or the geometric center of the area under the loading diagram. Okay. There's a detailed integration technique for this, but we're not going to worry so much about this because we're going to show you an example and how we can kind of apply this in a simple way. Okay. So let's go ahead and do an example now. So I'm going to go ahead and draw this example out for you. We have a beam, and the loading on this beam is going to be a little different than the one I had shown you, the general loading. We're going to kind of have this curve that looks like this, and we're going to define this by W equals 60x squared in newtons per meter. And then I'm going to say that the total length of the beam is 2 meters. And we're measuring, of course, from the starting point X. Okay. Now what we're going to do, basically, is we want to determine the magnitude and location of the equivalent resulting force acting on this shaft here. Okay. I also want to give the value here, the max value here we have is 240 newtons per meter. Just have to plug that in to get that, okay? Now, let's go ahead and solve for this. So, we have W, this is W of X, this is a function of X. We're going to solve this by integrating because we have already W as a function of X. So, what we're going to do is we're going to say that the positive is actually down for FR, and this is equal to the sum of all forces on the element, okay? So, FR is equal to the integral of A dA. That was the equation I had written for you previously. So, the integral from 0 to 2 of 60x squared dx. When I integrate this, I get 60x cubed over 3 from 0 to 2 meters, and I end up getting 160 newtons. This is the value of my resultant. Now, I'm not done because I also need the location of the resultant. So that's the value. I want to now find the location of the resultant. So I'm going to measure it from this starting point here. And I'm going to say x bar equals, I'm going to rewrite the formula, integral of a x dA divided by the integral of just a dA. And that's equal to the integral from 0 to 2 of x times now 60x squared. That was the W I was given. Divided by just 160, right? That's my FR. So I don't need to do anything. Just divide it by the FR that I got. So I get 60x to the 4th divided by 4 integrated from 0 to 2 divided by 160. And I end up getting 1.5 meters. Okay? So the resultant force acts here 1.5 meters away from that starting point and has a value of magnitude of 160 newtons. And that is my answer. Now, I want to go over some common types of distributed loads that we typically deal with. The first one is a constant distributed load. So, if I have a beam element, I'm just going to draw a simple supported one here. We often have constant distributed loads, which we draw like this, which means that they don't change. So we don't need to define this, right, by a function of x. This would just be like 10 pounds per foot, 10 kips per foot, anything like that, right? So this just is a very simple and straightforward type of distributed load. We also deal with triangular distributed loads. So if this is, again, just going to draw a simply supported beam element, triangular distributed load could look like this. We start from 0, and we have some magnitude of your of your triangular distributed load here. This could be any value up here. And this is another type of distributed load that we often see in engineering applications and civil engineering applications. We don't deal with too complex of loads very often in civil engineering applications, so it's good to remember these common types. Okay. Now that you know, or that you've had a little bit of a refresher on distributed loads, try this practice problem on your own and see if you can solve for the resultant force and figure out where it acts.